Hello everyone, welcome to Basics e-learning.
In lesson number 5 video, I am going to discuss the Z transforms of most useful sequences. So these sequences can be directly used in problems where you have to find out the Z transform of any big problem. So this transform, that is the sequence transform, directly you can use in Z transform like a formula. So I'm going to explain all these sequences here. In my previous videos, you can see the introduction to Z transforms and also the properties of Z transforms. I'm going to leave a link in the description box. Please go through that one. The first sequence that we are going to find the Z transform is unit impulse function. So as you all know, unit impulse function is defined like this. An impulse that may be a continuous time signal or discrete time signal. Remember, Z transforms are applied only on discrete time signal. So that's why the heading itself is some of the useful sequences, right? Not the signal, right? So signal means it's a continuous signal. For discrete time, we call it as sequence because it is a train of impulses, right? So that's why these are called here sequences. Coming to the impulse function, here it's a single pulse that may be a continuous time signal or a discrete time signal. It's a single pulse at t is equal to 0, or as it is a discrete time signal, it is defined at n is equal to 0 and is represented as del of n. So here the signal del of n is represented as 1, right? Unit impulse 1, defined as 1 at n is equal to 0 and is equal to 0 elsewhere, right? So this is how an impulse function is defined. Now I have to find out the Z transform of this impulse function del of n. So let us call x of n is equal to del of n here. So by definition, I know x of z is nothing but sigma n is running from minus infinity to infinity, x of n z power minus n. As x of n is del of n now, I replace x of n as del of n here. So n is running from minus infinity to infinity, del of n z power minus n. If you see here, this function is defined for minus infinity to infinity. But coming to the definition of del of n here, it is defined only at n is equal to 0 here. Elsewhere it is 0. So the summation can be reduced here like this. See, this is nothing but 1, right? The value of del of n is 1 here, right? So 1 when it is n is equal to 0. Elsewhere, so at n is equal to 0, if you are taking, it is 1. So the remaining, it is 0, right? So del of n value is 1 here. So I can write 1 z power minus 0, or else more clearly you can write it like this. You can expand this from so on plus z del of minus 2 z power minus 2, minus of minus 2, that will be plus 2, plus del of minus 1 z of z power minus of minus 1 plus 1, plus del of 0 z power 0, plus del of 1 z power minus 1. So like this we will expand. So if you see here, it is defined only this part, right? So only this function exists. Elsewhere it is 0. Del function is 0 elsewhere. So this is defined only at n is equal to 0. So this summation will lead to only del of 0 multiplied by z power 0. So this is minus 0, right? So del of 0 is nothing but 1. 1 z power 0. So that is nothing but 1, right? So 1 at any z value. So the ROC is entire z plane as it is a numerical, right? So ROC is entire z plane. So here the Z transform of unit impulse function is nothing but that Z transform of del of n is defined as 1, right? So this is how the impulse function is defined here. So we have seen the Z transform of x of n, that is nothing but the Z transform of del of n here is defined as 1. Now let us see the variation of this, that is the shifted version of your impulse function. So this del of n is defined only at n is equal to 0 with magnitude 1. Suppose if it is shifted to your left side or right side, what happens to the Z transform? That also we will see. Suppose say the signal is defined as del of n minus n naught, right? That is, it is shifted. Now let us say here this is only the signal. Now let us find out x of z. X of z is sigma n is running from minus infinity to infinity, x of n z power minus n. That is nothing but I'll replace my x of n with the required signal, that is del of n minus n naught z power minus n. Now you expand this one, right, over minus infinity to infinity. If you expand, the term only you're getting here is, see, what is del of n minus n naught? Del of n minus n naught is nothing but 1 when n is equal to n naught. So the signal will exist only at n is equal to n naught. Now expand this for more understanding, right? Suppose here del of, right, I'll write 2 minus n naught z power minus of minus 2, right? So that will be 2 plus z del of 1 minus n naught z power 1 plus del of 0 minus n naught, right? Like this it will. So which term it will be remaining? This is defined only at n is equal to n naught, means only this term will be remaining, right? So that is when n is equal to n naught, this will become, right? So z power n naught it will come, right? So that is nothing but here z power minus n, right? So when n is equal to n naught, what happens here? So z only you will get it as z power minus n naught, right? Only the magnitude will be 1 as usual, right? Because this is delta function. So instead of z power minus n, I'll get z power minus n naught because n is equal to n naught. And this n naught will depend upon where the signal is defined here. Whether it is shifted to 2 units, 3 units, 4 units. So this minus n naught, that n naught is here the shift in your signal. That is the impulse signal. So Z transform of this signal is defined as Z power minus n naught, right? Similarly, if the signal is del of n plus n naught, then the Z transform is defined as Z power plus n naught, right? So if it is a plus shift, then you will get the plus n naught. If it is minus n naught, then you will get minus n naught, Z power minus n naught, right? So this is how the Z transform is defined for the impulse function and its variations. Next sequence that we are going to find Z transform is unit step sequence. See, all these basic signals already I have explained in the first 15 lectures of signals and systems basics. So that which covers all the concepts there. So that link also I am going to leave in the description box here. So here the unit step sequence, right? It is unit step sequence means indicated with u of n. So it is defined like this. U of n is 1 when n is greater than 0, right? As this is a discrete time signal, this is n, this is u of n, right? So u of n by definition, unit step sequence is u of n is equal to 1 when n greater than or equal to 0 and is equal to 0 for n less than 0. Means it is a positive side sequence, right-handed sequence, right? So we will see what is this sequence, right? The Z transform of this sequence we'll see. So already in the previous video, I think second video of Z transforms, I have explained if x of n is equal to a power n u of n, this is nothing but a positive sided sequence, positive time exponential time sequence. There I have did this derivation part also, right? So there x of z is defined as z by z minus a. So if you can bring a similarity between these two signals, see here there is no 1, right? So a power n, where here a is 1 here, right? So x of n, you can write it as a power n u of n is z by z minus a. If you can assume a is equal to 1, that is nothing but x of n is equal to u of n, right? That is the required signal where we are trying to find out the Z transform. So if you put a is equal to 1 in this sequence, then x of n it becomes a of n. Then the Z transform also you keep a is equal to 1 here. So you will get x of u of n. Sorry, Z transform of u of n here is defined as z by z minus 1. For this, your ROC is here, as it is a positive side sequence, mod z greater than mod a. As in place of a here you have 1. So your ROC is mod z greater than 1. So this is how you can remember the unit step sequence Z transform. Similarly, it is very important to remember the negative time unit step sequence also. That is the left hand side sequence. That is u of minus n, right? Minus u of minus n minus 1, right? So this is your signal. So here x of n is defined as minus u of minus n minus 1, which is defined for n less than 0, right? That is n is equal to 0 is defined for positive sequence. So that is this signal starts from n is equal to minus 1. So if you consider this signal, what will be your Z transform? As we know, the negative sequence, right? So negative time exponential sequence, if you are taking x of n is equal to minus b power n u of minus n minus 1, there the Z transform is defined as z by z minus b, where the ROC is mod z less than mod b, right? So if you can bring a similarity here, if you are taking b is equal to 1, this x of n becomes u minus u power minus n minus 1, right? So then the Z transform also you can relate it. So that the Z transform I can write Z transform of minus u of minus n minus 1 is nothing but z by z minus 1, where ROC is mod z less than 1, right? So this is the Z transform of negative time unit step sequence. This is also very important that we are going to use these formula further in problems. Next sequence is sinusoidal sequence. So here I am going to find the Z transform of a simple sinusoidal sequence. So the signal x of n here, the sinusoidal signal is defined as sine omega naught n u of n, right? So here instead of writing the regular omega, I am writing this omega. So as this is a discrete time signal, the velocity, right, the angular velocity is defined like this only with this omega, right? Remember. Now x of z I am going to find out the Z transform of this sequence, where x of z is defined, sigma n is running from minus infinity to infinity, x of n z power minus n. So substitute x of n with your required signal. So here I am going to find sinusoidal signal. So I am writing sine omega naught n u of n z power minus n. If you observe here, u of n is a unit step sequence which is defined only for the positive sided sequence. So instead of writing the summation will reduce now to sigma n is running from 0 to infinity. Minus infinity to 0, u of n is 0. So the entire thing will go to 0. So only this is defined for n is equal to 0 to infinity. Sine omega naught n, u of n will become 1 here. So in this limits, that is n is running from 0 to infinity, your u of n is 1. So I am not writing that. Z power minus n. Now let us take this. Here sin theta can be written as e power j theta minus e power minus j theta divided by 2j. So I am just writing this sine omega naught n in this format. So let us write that. See here, sigma n is running from 0 to infinity. Instead of theta I have omega naught n here. So I am writing that e power j omega naught n minus e power minus j omega naught n divided by 2j multiplied by z power minus n here, right? Now you can write this z power minus n, I am just multiplying. and 2j will not do anything with the summation. So I am writing 1 by 2j outside. Sigma n is running from 0 to infinity. Observe the derivation properly. It's a bit lengthy but easy only. So I am doing step by step here. So here e power j omega naught n multiplied by z power minus n. I am just multiplying z power minus n with each term inside the braces here. So e power minus j omega naught n z power minus n. Right? So this is how it is simplified. Now let us see how you can simplify it more. So see here. 1 by 2j, right? So sigma n is running from 0 to infinity. This I am writing e power j omega naught z power minus 1 whole power n. That is n I am writing outside, right? So minus e power minus j omega naught z power minus 1, right? Whole power n, right? So if you multiply this n, we are taking common out here, right? So this is what I am getting till now. Now, if you consider these two terms, these are like with the infinite summation formula, right? That is sigma k is running from 0 to infinity. A power k can be written as 1 by 1 minus a. If you see here, these two terms have the similar summation. N is running from 0 to infinity and whole power n, right? So k is running from 0 to infinity, a power k. So in place of a, I have e power j omega naught z power minus 1 and e power minus j omega naught z power minus 1. So these two terms can be expanded like this. So 1 by 2j multiplied by 1 by 1 minus e power j omega naught z power minus 1, right? 1 by 1 minus a format, right? So minus, again this one also I can write it as 1 by 1 minus e power minus j omega naught z power minus 1, right? So now to find out the Z transform, you know that Z you have to write it up, right? So if you can do that, you will get it like this. To bring it in the regular form, what I am doing is multiply and divide with Z, both the numerator and denominator. So what we'll get? 1 by 2j Z by Z minus e power j omega naught. This Z power minus 1 and Z will get cancelled. Minus Z by Z minus e power minus j omega naught, right? So now you can take LCM to simplify it more. So this will be Z minus e power j omega naught multiplied by Z minus e power minus j omega naught. So that can be written as Z multiplied by Z minus e power minus j omega naught minus Z multiplied by Z minus e power j omega naught. So let us simplify this more. Further, it can be simplified like this. I am just multiplying the numerator and denominator terms. So z into z, it is z square minus z e power minus j omega naught minus z square plus z e power j omega naught. So here in the denominator also, you can multiply each and every term with each and every other term here. So z square minus z into e power minus j omega naught minus z into e power minus plus j omega naught minus into minus plus e power j omega naught into e power minus j omega naught. Let us see, z square will get cancelled here. So what I am getting is minus z e power j omega naught, right? So here this can be written as, if you can take z out in the numerator, what you are getting, e power j omega naught minus e power minus j omega naught, and this 2j is there, no, that you take it up like by 2j, right? This is what I am getting in the numerator. And in the denominator, why I am writing this is again in the sign form, right? E power j theta minus e power minus j theta by 2j, right? Coming to the denominator, this is 1 here, e power theta multiplied by e power minus theta, that is 1 here. So you can write, you can more simplify. Again, see here, these two are like cos, right? So cos omega naught can be written as e power j omega naught plus e power minus j omega naught, right? So here if you take z out, it will be that form. So z square minus z if you are taking common, then you will be getting cos omega naught by 2 also there. So I'll just multiply and divide with the 2 to bring it in that form. So minus 2z into cos omega naught plus 1, right? So coming to the numerator, this is of the sine form. So finally it can be written like this. See, z sine omega naught divided by z square minus 2z cos omega naught plus 1. So this is the Z transform of your simple sinusoidal signal in a discrete time domain. So if you remember these Z transforms of these simple sequences, directly you can apply in for problems without doing all these derivations again. So directly you can use this formula in the problem. Similarly, the Z transform for the cosine signal is also defined. See, x of n is equal to cos omega naught n, u of n is the cosine signal. Then the Z transform of such cosine signal is defined as z square minus z cos omega naught divided by z square minus 2z cos omega naught plus 1. So this is also another important sequence. And the last sequence in today's video here is unit ramp sequence. So we know the ramp signal is defined like this. X of n is equal to n into u of n. That is, the signal is like this for continuous and defined like this for discrete. That is, when n is equal to 1, the amplitude is also equal to 1. When n is equal to 2, the amplitude is also equal to 2. When n is equal to 3, amplitude is equal to 3, like this, right? So now let us find out the Z transform of such sequence. X of n is equal to, every time try to write down the formula so that it will be memorized. So x of z is defined, sigma n is running from minus infinity to infinity, x of n z bar minus n. As I am trying to find out the Z transform of this unit ramp sequence, I am replacing that with n into u of n z bar minus n. As the signal is defined for u of n, instead of n is equal to minus infinity, you can take it n is equal to 0 to infinity n into z bar minus n, like in the previous case, right? So now see, this is like a infinite sequence form, right? So this you can write 0 to infinity n into z bar minus 1 whole power n. If you observe, this is of the form sigma n is running from 0 to infinity n into a power n, infinite sequence. So this sequence can be expanded a by 1 minus a whole square. So instead of a, I have z power minus 1 here. So if you write it in that format here, what we will get here is, instead of a by 1 minus a whole square, you can write it z power minus 1 divided by 1 minus z power minus 1 whole square. So it can be further simplified. See here, this 1 by z you can write it, right? So that when you write it 1 by z, 1 by, or else you do one thing, as I have this square, you just multiply with z square on both the sides, numerator and denominator. Then it will become z divided by z minus 1 whole square, right? So this is the Z transform of unit ramp sequence. So the Z transforms of all the important sequences I have tabulated here. So already we have done the derivation part. So this is the description here. See, for unit impulse signal, that is del of n, the Z transform is 1. So ROC is entire Z plane. The shifted version, del of n minus n naught, del of n plus n naught. If you have minus here, it will be z bar minus n naught plus z bar plus n naught. So like this is a positive side sequence, so that's why it is mod z greater than 0. it's a negative side. The del of n is on your left hand side. So that's why it is mod z less than infinity is your ROC. Second sequence is unit step. Unit step signal is defined both again for negative side and positive side sequence, u of n and u of minus n minus 1. For both the sequences, Z transform is Z by Z minus 1 only, but the ROC is different here as you are taking in the form of Z by Z minus A. So mod Z is greater than A. This is Z by Z minus B. So mod Z less than B format. In place of A, I have 1. In place of B, I have 1. So here ROC is mod Z greater than 1 and mod Z less than 1. Coming to sinusoidal signals, sin omega naught and u of n. So the Z transform is Z sin omega naught divided by Z square minus 2Z cos omega naught plus 1. For cos omega naught and u of n, Z square minus Z cos omega naught divided by Z square minus 2Z cos omega naught and omega naught plus 1. So for both ROC is mod Z greater than 1. So if you observe here, the Z transform of both sin and cos, the denominator is same here. Z square minus 2Z cos omega naught and omega naught plus 1. Whereas the numerator, if it is sin, it will come as in the form of Z sin omega naught. If it is cos, Z square minus Z cos omega naught. Then for unit ramp, n into u of n is the sequence. So the Z transform is defined Z by Z minus 1 whole square. As in the denominator it is Z minus 1. So Z minus 1 greater than 1. So mod Z is greater than 1 is the ROC for this sequence. So students, try to remember all the Z transforms of these sequences. These are very important. So once you remember, you can apply it in the problems very easily.
For more videos, please do like, share, subscribe to our channel. Let us know your suggestions and queries in the comment box. Thank you.